Alright, hello everyone, and welcome to Lesson 4 in Unit 8 for AP Chemistry, which is on acid-base reactions and buffers. At the end of this video, you should understand that acid-base reactions involve proton transfer and are governed by equilibrium. When a strong acid and strong base are mixed, they're going to react completely to form water, and the pH of the final solution is determined by whichever reactant is in excess. You will also learn that when a weak acid reacts with a strong base, they neutralize to form the conjugate base and water. If the weak acid is in excess, a buffer forms and pH is calculated using the Henderson-Hasselbalch equation, which we will go over in 8.9. If the strong base is in excess, pH is determined from the leftover OH-. If equal amounts react, the solution becomes slightly basic due to the conjugate base reacting with water. And finally, you will learn that when a weak base reacts with a strong acid, they neutralize to form the conjugate acid and water. If the weak base is in excess, a buffer forms and pH is calculated using the Henderson-Hasselbalch equation. If the strong acid is in excess, pH depends on the leftover H3O+. If equal amounts react, the solution is slightly acidic due to the conjugate acid. When a weak acid and a weak base are mixed, they establish an equilibrium between all of the species. Let's start by going over what happens when you mix a strong acid with a strong base. So we know when we're talking about strong acids or strong bases, that means we have 100% dissociation into its constituent ions. So for example, when we have sodium hydroxide, which is a strong base, and we dissolve that into water, there will no longer be a formula unit of NaOH. There will be separate Na plus and OH minus ions. Same with a strong acid like HCl. When we dissolve that in water, we'll no longer have molecules of HCl. We'll have H plus and Cl minus. Now, because all of our strong acids start with hydrogen and all of our strong bases end with hydroxide, when those ions break apart and we have OH minus and H plus, those are going to form water. And then what's left over are your cations from the base and your anions from the acid, and those will make a salt. So in this case, that would be NaCl. And we know that NaCl does dissolve in water. So from here, if you want to see why all strong acid and strong base reactions make this net ionic equation, let's go ahead and write out the complete ionic equation. So we have Na plus OH minus plus H plus Cl minus reacts to form water. Remember, if it is not aqueous, it stays together. So this liquid stays whole. It's not broken apart. And then we have Na plus and Cl minus. So you can see that sodium and chlorine are our spectator ions here. So our final net ionic equation would be OH minus plus H plus reacts to form H2O, and that happens for all strong acid and strong base reactions. Now, what happens with pH? So if we have the perfect amount of sodium hydroxide and hydrochloric acid, and we have the same number of moles of those, then the pH is going to be 7 because they're going to neutralize each other perfectly. However, let's say we have more NaOH left over at the end, then we're going to have a slightly basic solution because we'll have a little bit more NaOH left over. Same goes for acid. If you have a strong acid and a strong base reaction, but you have a little left over HCl, then obviously you're going to have a pH lower than 7. So now let's do another example. We have sulfuric acid, which is H2SO4 that is dissolved in water, so aqueous. And then we have lithium hydroxide, which is LiOH, again aqueous. Our H from sulfuric acid and our OH from lithium hydroxide is going to make water. And we know that's in liquid form. And then our lithium and our sulfate will bind together as an ionic compound or a salt. So lithium is a positive 1 charge, sulfate is negative 2, so we need 2 lithiums to balance out that sulfate. So now we need to balance that. We have 2 lithiums on the right, so I'm going to put a 2 in front of lithium hydroxide, which means total on the reactant side I have 4 hydrogens, so I need to multiply H2O by 2. So now we can go ahead and write out our full complete ionic equation. And we can see our spectator ions are the lithium and the sulfate. And then we're left with the following, which simplifies down to let's do a practice problem with a strong acid and strong base. So it says, what is the pH? So I'm solving for pH after the addition of 10 milliliters of 0.1 molar NaOH to 25 milliliters of 0.1 molar HCl. So let's start with our equation. We have sodium hydroxide reacting with hydrochloric acid. That is going to form water and salt. So because everything is a 1-to-1 ratio, let's solve for the moles of our strong acid and strong base and find out what is going to be limiting the amount of water and NaCl that we can make. So we know the equation for concentration is moles per liter, so we can rearrange that to solve for moles. So moles equals concentration times liters. So we are already given concentration. So starting with NaOH, our concentration is 0.1, and then we need to convert 10 milliliters into liters. So that is going to be 0.01 liters. So that's going to give us 0.001 moles of NaOH. And now we're going to do the same thing for HCl. So we're starting with, again, 0.1 molar, but this time we have 25 milliliters, so that'd be 0.025 liters. So for that, we get 0.0025 moles of HCl. So going back to our original idea of limiting reactants, if all of this is 1-to-1 ratio and we have less NaOH, the NaOH is going to run out first. So NaOH is going to be our limiting reactant. So we're going to have excess HCl. And because we're going to have excess HCl, we can assume that the final pH is going to be acidic. So keep that in mind when you're checking your work at the end. All right, so now what do we do with this information? So again, everything is 1-to-1 mole ratio, so it makes this nice and easy. I know if I'm starting with 0.0025 moles of HCl and I have to use up 0.001 to form my products and neutralize that NaOH, I'm going to be left with 0.0015 moles of HCl. And when I'm trying to solve for pH, I know I need H plus or H3O plus, and I know that is a 1-to-1 ratio here. So I know that that's going to be 0.0015 moles of H plus. So I'm getting really close to being able to solve for my pH, but I know to solve for pH, I need concentration of H plus. Sorry about that, guys. So to get concentration of H plus, I take my moles and put it over the total volume. So I know I started with 10 milliliters and 25 milliliters. So adding that up, that would be 35 milliliters, which is going to convert to 0.001 0.035 liters. So now I can take this number, divide it by 0.035 liters, and that's going to give me my concentration of H plus, which is 0.0429. So now that I have that, I can solve for pH. So negative log of the concentration of H plus, which is 0.0429. And that is going to give me a pH of 1.37. And that is my final answer. All right, before we get into our next type of reaction, I want to go over what a buffer is first, so you're not completely confused when I'm explaining it. So a buffer is a solution that resists pH change when a small amount of acid or base is added. And that specific part, small amount, is important because buffers have its limits. After you add too much acid or too much base, it's obviously going to overcome that buffer and just reduce or increase the pH, depending on whether you're adding acid or base. So a buffer is going to exist when you have a weak acid with its conjugate base or a weak base with its conjugate acid. And what I mean by that is, let's say we have hydrofluoric acid reacting with sodium hydroxide. So that's a weak acid with a strong base. That is going to make water and sodium fluoride. Now, when we break this apart, hydrofluoric acid does not dissociate, so it stays together. That's our weak acid. Sodium hydroxide does dissociate, so we now have Na plus and OH minus. Water stays together, and then sodium fluoride dissociates into its constituent ions. So our sodium, in this case, would be our spectator ion, and we are just left with the following net ionic equation, which is exactly what is shown here. So when that happens, we can see that we are left with our weak acid, HF, and its conjugate base, F minus. And if we're looking at what happens when a weak acid is established in equilibrium, we know that HF is going to be reacting with water, and it's going to be slightly dissociating into H3O plus and F minus. And remember, we can write this more simply without the water, and it could be written as HF reacts to form H plus F minus. So this is this, and this is this. So just real world examples to go along with what it's saying in the image. So now I have this weak acid and conjugate base in solution. I have both of them there. And essentially what a buffer is if I add acid to this solution, the conjugate base, F minus, is going to neutralize that acid and shift the equilibrium back towards HF in order to offset that pH and balance it out, just like we learned about in Le Chatelier's principle. And that's all a buffer is. So it also could go in the opposite direction. If we were to add OH minus, then we're going to neutralize this H plus by making water. And if we are decreasing H plus, then it's going to shift towards that substance. So we are going to be making more of our conjugate base, which is why we're shifting equilibrium and offsetting that pH. I know buffers can be very intimidating when we're first learning about them, but let's break them apart a little bit more so hopefully we can grasp that understanding a little easier. So let's start with when we are reacting a strong acid to a weak base. First, whenever you see this type of interaction, I want you to immediately be thinking that the pH is going to be lower than 7, because obviously our acid is going to be stronger than our base, and because that acid fully dissociates, we will have more H3O plus or H plus ions in solution, which is why that pH is lower. Now, the second thing I want you to think about whenever you have a strong acid mixed with a weak base is what is left over at the end. Meaning, if you have more weak base at the end than you do strong acid, so all of your strong acid was consumed, that means you have a buffer solution, because now you have an equilibrium that includes your weak base and your conjugate acid. And that is where the buffer comes into play. So let's start out with an example. So we have hydrobromic acid, which is HBr. That is a strong acid, so it fully dissociates. And then we have ammonia, NH3. And that is a weak base. So we know hydrobromic acid is an acid, so it's going to donate its proton. And then ammonia is a base, so it's going to accept the proton. So we're going to form NH4 plus and Br minus. Now let's go ahead and write our net ionic equation. To do that, we need to form our complete ionic equation by separating everything that we can, which is only going to be HBr, because we cannot split up NH3 because it is a weak base. So weak bases do not dissociate, so those are going to stay the same. And then NH4, already an ion, Br minus, already an ion. So now from here we can see that Br minus is our spectator ion. So our net equation is H plus NH3 reacts to form NH4 plus. So this here is our buffer. And the reason it's our buffer is because when you add a little acid to this, for example, we are going to be increasing the amount of H plus ions we have in solution. And because of Le Chatelier's principle, it's going to shift to the products to offset that pH change. So if we only add a little bit of acid, that shift in equilibrium is going to offset the pH change. Now it's kind of the same concept when we're adding a little bit of base to this buffer. If we add a little bit of base to this buffer, we know that we are adding OH minus. And when we add OH minus, it now reacts with the H plus to form water. And because we are forming water, we are decreasing the amount of H plus, which means, because of Le Chatelier's principle, we are now going to be shifting the equilibrium towards the reactants, which again is going to offset that pH change. So if you just add a little bit of base, nothing really is going to happen. All right, now let's do the same thing, but with a weak acid and a strong base. So when we have a strong base, again, that is going to be 100% dissociated. So we're going to have many more hydroxide ions than we would hydronium or H plus ions. So that is why the pH is going to be greater than 7, because it will form a basic solution. Now, when we're talking about buffers, in this specific scenario, if all of the strong base is used up to neutralize the acid, and we are left over with weak acid, that is when we have a buffer, when the weak acid is in solution with its conjugate base. So let's go ahead and start out with an example, because I always think that helps. We have acetic acid, which is our weak acid, CH3COOH. Then we have our strong base, which is barium hydroxide, so BaOH2. And remember, strong acids are going to completely dissociate. Then our acetic acid is going to donate a hydrogen, and it's going to be left with acetate as the ion, and that is going to bond with barium, the cation. So it's going to be Ba, because Ba is 2+, I'm going to need 2 of these acetates. And then I will have water left over. So the hydrogen from acetate and the hydroxide from barium hydroxide. And then we need to balance our equation. So I need 2 of my acetic acids, and then I need 2 waters. So now that we have that, let's go ahead and make our complete ionic equation. So because we have a weak acid with a strong base, the strong base is going to be the only reactant that is separating or dissociating, and then our barium acetate will also dissociate because it's an ionic salt. So when we do that, we have Ba2 plus as our spectator ion, so that gets canceled out. And then everything has a coefficient of 2, so I'm going to reduce that to a coefficient of 1 for our net equation. And this here would be our buffer solution. So if we were to add base to this buffer, that means we would be increasing the amount of hydroxide ions we have. So in order to offset that pH change, according to Le Chatelier's principle, if we're increasing a reactant, we're going to be shifting towards the products. And then if we add acid to this buffer, then the acid will have H+, which means this will react to form water, which takes away that OH-. So we're reducing the reactants, which means we're going to be shifting towards the reactants to offset that pH change, and that is the buffer in action. All right, so let's do a practice problem with a weak acid and strong base. If 100 milliliters of 0.1 molar acetic acid is added to 100 milliliters of 0.1 molar potassium hydroxide, calculate the pH of the resulting solution. So let's go ahead and start off with our equation. So we know that acetic acid is reacting with potassium hydroxide, and the acetic acid is going to separate slightly into acetate and H+ ions, and the KOH is going to separate completely into potassium ions and hydroxide ions. So we know the hydrogen and hydroxide are going to react to form water, and then we will have potassium acetate. And then if we wanted to do our net ionic equation, KOH is going to completely dissociate, and so is our ionic salt. So potassium is going to be our spectator ion, and we're going to be left with acetic acid, hydroxide reacting to form water, and acetate. So now that we have that equation, let's go ahead and figure out how much acetate we are making. So I know I have an acid and a base. If an acid and a base is neutralized, it means I have the same number of moles of each. So let's figure out how many moles of my 2 reactants I have. So first, starting with acetic acid, I have 0.1 for my concentration and 0.1 for my liters of solution. So capital M times volume is going to give me moles, so it's going to be 0.01 moles of acetate. And then for potassium hydroxide, I have, again, 0.1 concentration and 0.1 volume, so it's going to be 0.01 moles of KOH. And since there's only 1 hydroxide in there, that also means I have 0.01 moles of hydroxide. So again, because this is an acid-base reaction, we need equal moles to neutralize. So because I have the same number of moles of my two reactants, that means I'm going to completely use that up, and it's a 1-to-1 ratio, which means I'm then going to end up with a concentration, with number of moles of 0.01 of acetate. So now that I know that my acid and my base completely neutralized to make my acetate, I now have a starting point to solve for Kb and to use Kb to solve for my concentration of hydroxide. So we know that Kb is a base which produces hydroxide. So we're actually going to flip this equation when we are starting to solve for hydroxide concentration. So we're now going to make the products reactants, so H2O plus acetate reacts to form hydroxide and acetic acid. So up here was for Ka, and now here is for Kb. So now that we are doing Kb, this is the exact same math that we did in 8.3. So it just required that initial step to get to that point. So we are starting with a concentration of acetate. I forgot the negative here. So we're starting with a concentration of acetate, which we need to figure out. We have 0.01 moles, and in order to get that to concentration, we need to divide that by total volume, and we have 200 total milliliters. So 100 plus 100. So we're going to divide that by 0.2 liters. So 0.01 divided by 0.2 is going to give us 0.05 concentration. So we are starting with a concentration of 0.05. We are not including water because that is a liquid. We are going to be losing acetate, so it's going to be 0.05 minus x, and we are starting with 0 here and gaining our products. It's going to be x and x. And remember we talked about in the last lesson, we can go ahead and lop this off when we're solving. So now that we have everything to plug in to Kb, so we know Kb is equal to the concentration of our products over the concentration of our reactants. I now figured out that my products are going to be x times x, which is x squared, and then I'm just going to put 0.05 here. Now, in order to solve that, I have to have my Kb value. Now, how would you get your Kb value? Well, on your reference sheet, you are given this. Now, we already have Ka. We also already have Kw because it is a constant on your formula sheet. So because of that, we can go ahead and solve for Kb by taking Kw and dividing Ka. So that's going to be 1 times 10 to the negative 14th, that's Kw, over 1.8 times 10 to the negative 5th. And that is going to be our Kb value. And for Kb, I get 5.56 times 10 to the negative 10th. So now that I have that, and it's equal to my expression, I can go ahead and solve for x. And remember, x is going to give me my concentration of hydroxide ions. So solving for x, I'm going to get 5.2 times 10 to the negative 6th. And then from there, that means I have concentration of hydroxide ions. So I can go ahead and solve for POH, which is the negative log of my concentration of OH minus, and I do have that. So negative log of 5.27 times 10 to the negative 6th. That is going to give me a POH of 5.28. However, it is asking for pH, so we need to take 14 minus 5.28, and that's going to give me my final answer of 8.72. All right, so we've gone over strong acids and strong bases. We've gone over strong acids and weak bases, and then we've gone over strong bases and weak acids. Finally, we have weak acids and weak bases. And when they react, the reaction is going to be reversible, and it's going to establish an equilibrium, producing both a conjugate acid and a conjugate base. And the final pH is going to depend on the relative strengths of Ka versus Kb of the acid and the base. So let's go ahead and practice writing one out. So we have acetic acid, which is CH3COOH. And then we have ammonia, which is NH3. NH3 is a base that's going to accept a proton. This is going to end up being NH4 plus. And then we're going to have acetate, CH3COO minus. So our acid and our base are weak, so they're not going to dissociate. So this is the equation. We don't do anything with it. Nothing can dissociate into constituent ions. All right, so now that we've gotten the content out of the way, let's go ahead and do some practice problems. The first one says addition of sulfurous acid, which is hydrogen paired with sulfite, SO3, 2 minus. That's why we need 2 hydrogens. So sulfurous acid reacts with barium hydroxide, so that's BaOH2. And it says it forms a precipitate. So we have the hydrogen reacting with the hydroxide to form water. And then our precipitate is the solid, insoluble ionic compound between barium and sulfite. So they're both 2 charges, so BaSO3. That's going to be a solid. So for net ionic equation, liquid and solid does not dissociate. Weak acid does not dissociate. The only thing dissociating is barium hydroxide because it's a strong base. So everything will be the same except we will have Ba2 plus and 2 hydroxides. And so the answer for this question, oh, and balance, sorry, forgot to balance that, H12. So the answer to this question would be B. All right, so a student mixes 40 milliliters of 0.1 molar HBr with 60 milliliters of 0.1 molar KOH. What is the concentration of hydroxide in the resulting solution? So we've done a couple of these. I'm going to not do states of matter because I'm feeling lazy, but make sure you do those on the final exam. So H and OH are going to make water, and then K is going to bond to Br for an ionic salt. So we know that strong acid, strong base, 100% dissociation. So we'll have H plus Br minus plus K plus OH minus reacts to form water, K plus, and Br minus. Now I'm just doing this to show you how we get it. Obviously, if you have a strong acid and a strong base, you should already know that the net ionic equation will be H plus OH minus reacts to form water. So if you want to just start with that, that is totally fine with me. So now I need to figure out, do I have the perfect amount of each of my acid and base to make my product, or am I going to have something left over? So first let's start out with the moles of each. So for HBr, to find moles, I'm going to multiply concentration 0.1 times volume in liters, which is 0.04. That's going to give me 0.004 for HBr. And then for KOH, I have 0.1 times 0.06. That's going to be 0.006. So HBr is going to be my limiting reactant. So if I'm looking at KOH, I'm starting with 0.006 moles. Because I have to use 0.004, I'm going to be left with 0.002 moles of KOH, which is equal to 0.002 moles of hydroxide ions. Now that I have 0.002 moles of hydroxide, I can get concentration of hydroxide by dividing it by the liters. And I know I have 60 plus 40 milliliters, which is 100 milliliters, or 0.1 liters. And so that gives me 0.02 molar OH minus, which is C. All right, so we have an acidic solution of HCl and HClO2. It's saying we add a bunch of KOH to get the pH up to 10.5, the amount of which of the following species increases as KOH is added. So first let's look at what happens to HCl when we add KOH. So HCl plus KOH, that's going to react to form water and KCl. So looking at the net ionic equation, HCl is a strong acid, so we're going to take that apart. KOH is a strong base, so we're going to take that apart. Water stays together. And KCl is a ionic compound that is also water. So as you can see, chlorine is not going to change because it is a spectator ion. So increasing KOH is not going to do anything to chlorine, so it's going to be an automatic cross out here. We are also getting rid of K+, which is not one of our options. And as you can see, our H+ is being consumed by the OH- in potassium hydroxide to form water. So we are actually decreasing an H+, and it's asking for what is increasing. So now let's look at our other reaction happening, which is with our weak acid, HClO2. And so that is again reacting with KOH, and that's going to form water and potassium there. So now let's go ahead and make our net ionic equation. This is a weak acid, so that does not dissociate. So HClO2 plus K plus OH minus reacts to form water, K plus, and ClO2 minus. So K plus is again our spectator ion. So what's happening here is we have our weak acid. It is being neutralized by that hydroxide, and we are forming ClO2 minus, which is our answer, and that is what we are increasing in this process. And we are using this up, so that's why this is not the answer. All right, when 200 milliliters of 2 molar NaOH is added to 500 milliliters of 1 molar HCl, the pH of the resulting mixture is closest to what? So we have a strong acid, strong base equation, which means I know my net ionic equation is going to be H plus OH minus reacts to form water. So first, let's start off with moles of H plus and moles of OH minus. So with H plus, I have HCl, and I have 1 molar HCl with 0.5 liters. It's going to be 0.5 moles of HCl, which is 0.5 moles of H plus. Now, looking at my OH minus, I have 2 molar at 0.2, which gives me 0.4 moles of NaOH, which is 0.4 moles of OH minus. So OH minus is my limiting reactant, so I'm only going to be left over with H plus, and I know if I started with 0.5 moles and I used up 0.4 because that's my limiting reactant amount, I'm going to be left with 0.1 moles of H plus. And in order to get that to concentration, I'm dividing it by total volume. So 200 milliliters plus 500 milliliters, or 0.7 liters. And 0.1 divided by 0.7 is 0.1429 concentration of H plus. So now if I want to get my pH is the negative log of concentration of H plus ions, which is 0.1429. That gives me a pH of 0.85, which is closest to a pH of 1. All right, what are the relative strengths of the acids and bases in the reaction represented by the equation above? So let's look at this equation. I'm going to identify my acid-base pairs. So here is one, and here is the other. So starting with acid, acid is a proton donor, right? This is being an acid by giving away a hydrogen, and this is an acid by giving away a hydrogen. So now I got to figure out which one of them is a stronger acid. Well, I know that based off the K value. So since my K value is less than 1, that means it is more reactant heavy, which means this HClO2 was a stronger acid because it produced more ions. So HClO2 is a greater acid than HCOO. So I know that A and B are both incorrect. So now moving on to my base strength. So a base is accepting a proton. So that would be going from this to this. And this to this. So again, the K value is telling me that I am making more reactants. So it makes sense for this blue base forming to be stronger because I am making more conjugate acid. So that means HCOO minus is going to be stronger than ClO2 minus. So the answer would be